Week 13, Part 4, Microscopes. So here are a couple of microscopes, an old antique one and a more modern one. And just some of the basic pieces of these. They have eyepieces, that's where you look in. And then they have objective lenses. And fundamentally, a microscope is just two lenses. Now, each of them is, in reality, a combination of a whole bunch of lenses. But they function just as a single lens in each place. Here are some pictures that show you the details of those. Here are the eyepieces composed of a whole bunch of lenses. And then down here are objective lenses of different magnifications. In a microscope, you change the magnification by changing the objective lens down here, and you leave the eyepiece alone usually. Each of these has a whole bunch of lenses in it, but once again, as I say, it functions effectively as a single lens. And the reason they put all of these other lenses together is to eliminate some of the troubling aberrations that they're called. And by putting combinations of lenses together, you can correct for the different distortions and color aberrations that come into play. So they look very complicated, but they still function essentially very simply. So here is more of a diagram of how a microscope works. And you see you've got just a single lens in each place. You can actually make a microscope this way. They don't work terribly well, at least if you try to get very much magnification, they don't. But here, this diagram is showing it with very, very low magnification indeed. But notice how the magnification happens between, here's the object down here that you're looking at, and this first lens creates an image of that right here. And you notice that it is, in fact, larger. It's also closer to the eye, much closer than you could even look at it very easily. But this second lens then is acting as a simple magnifier and taking the image that comes from that first lens and making that able to be seen by your eye. Notice that the rays coming into your eye are parallel. So those rays now are parallel, and so they seem to be coming from infinity. So your eye can easily focus on those. In fact, it's relaxed when it focuses on those. You can, if you wish, place a crosshair or scale of some kind right in here, a transparent slide with some little scale on it, and that scale will appear sort of superimposed right on top of the image you have of the object. So that's a useful way of seeing what's going on. And notice when you compare these two, here we've switched to a different objective that has a shorter focal length. Notice it's fatter in the middle, and it bends the rays more strongly. It has to be placed closer to the object, but it gets greater magnification. See how the image here is larger, even though the object is still the same size. So when you go to a higher magnification, you have to get the lens down closer to the object. Look up here at the eye, and you'll see you must position the eye at just the right place to intercept all of these rays. If your eye is either too close or too far away, you won't see everything. So you have to find that magical distance. It's called the eye relief. And if it's designed correctly, there's room enough even to be wearing your glasses and still look into the microscope. Now for a little bit more mathematical approach, let's see if we can work out the magnification of a microscope. So here's the same situation essentially. You've got the object over here. The objective lens creates an image of that here, and then the eyepiece lens brings those rays into the eye parallel. And if you look carefully at this figure, you can work it all out. Right here is a ray that went through the focal point, and therefore it comes out parallel. And we're going to make good use of some triangles in here. If you look carefully, right here, there's a section that is shown right there. So this H1, because this ray is also parallel to the optical axis, comes through this focal point, and then it goes through the image, the tip of the image right there. But this ray right here is the same as this ray here. And since this is parallel to the optical axis, then the height right there is the same as the height over here, which is just the height of the object. Call it H1 here. It ought to be HO, I suppose. And then over here would be the height of the image formed. And if you think about it, these two angles here must be the same. And so these triangles are similar triangles. And therefore, we can write this little relationship. And now you see I've changed from H1 and H2 to HO and HI. I just wasn't consistent here. But HO over FO, that would be the ratio of these two, is the same thing as HI over L. So these two have to have the same ratio because the triangles are similar. Now let's look at the, oh yeah, once we know that, then we can work out the lateral magnification. Lateral magnification is just the size of the image divided by the size of the object. So that's HI over HO. And from this relationship, we can see that that, in fact, is L over FO. The minus sign, I just have to stick in here somewhere because the image is, in fact, upside down. And so while these distances here you could say are all positive, we normally would write H2 or H image as if it were negative. So I just brought in the minus sign right here to reflect that fact that HI really should be a negative number. And so the formula should reflect that. So it's got to have this negative sign because in fact it is upside down. The magnification includes that minus sign. So this is the magnification of the first stage of the microscope. Now let's look at the eyepiece. And over here, this is just acting as a simple magnifier. We've got something here, and we're looking at it through an eyepiece. And with an ordinary simple magnifier, you get a magnification that's just this factor of 25 centimeters divided by the focal length of the eyepiece. Now all that's left to do is to put these two together, and we can do that by just taking the product of the two. Take the magnification of the objective times the magnification of the eyepiece, and you get the overall magnification of the microscope. And that's what this formula is. Note that it's negative again. The eyepiece didn't flip things around again, and so it's still upside down, and that's the way most microscopes are. When you look inside them, it often doesn't matter when you're looking at a microscope. If you're bothered by which way things are, you can rotate the object around and see it the way you want. But for most things, certainly in biology and other sciences, when you're looking at tiny little things, there isn't particularly an up direction that matters anyhow. So one doesn't normally bother about this. Though if you want, you can get special eyepieces that do flip it around. They have an extra set of lenses in them that turn the image around. Okay, let's do an example of this now. So now what I want to do is stop the share and switch cameras. So here we go. Here's an example. Let's say that we have a microscope with a tube length of 16. This L that I talked about in the formula, that's the tube length. It's the distance between the two focal points of the two lenses. And let's say it has a tube length of 16 centimeters. And if the eyepiece is a times 10 eyepiece and the objective is a times 30 eyepiece, that's what's usually written on the microscope. Then what's the overall magnification? Well, that's an easy question. Times 10 times 30 is times 300. That's going to be a magnification of 300. So that's the answer to part A. But what is the eyepiece focal length and what's the objective focal length? For that, you ought to look at the formula again. So what was it? It was minus L and then 25 centimeters divided by the focal length of the objective times the focal length of the eyepiece. Now what I'd like to do is point out, you can sort of divide up this formula into two pieces. And right here is the objective part, and here is the eyepiece part. So here is the magnification of the objective, and here's the magnification of the eyepiece. So if we want to get the focal length of the eyepiece, why, it's said to be times 10, and that times 10 must be 25 divided by the focal length of the eyepiece. So flipping this around, the eyepiece must be 25 divided by 10, or 2.5 centimeters. Again, that would be, this is all done in centimeters. 2.5 centimeters. So that's the focal length of the eyepiece. What about the focal length of the objective? Let's work that out. So we have this times 30 is equal to minus L over F objective. And right here, I have to point out that in general, when one is giving magnifications like this, you don't bother with the minus sign. Nobody bothers about it. So we'll just have to leave it out of our formula at this point, because the objective magnification should be technically stated as negative 30, but nobody ever does. Nobody bothers about that. So this is equal to 16 divided by the objective focal length. So 16 centimeters, that's our tube length in this case, if we happen to know it. And so switching this around, we'd find that the objective focal length is 16 divided by 30. And shucks, don't have that worked out here. It's going to be about a half, but let's see exactly what it is. 16 divided by 30. And I get 0.53. 0.53 centimeters, or one could write that as 5.3 millimeters. The focal length of the objective gives you a rough idea of how close the objective has to be to the object. Maybe it wasn't obvious from those diagrams that I made because they're made for such low magnification, but as you get up to high magnification, the object is very nearly at the focal point of that lens, and so that gives you a rough idea of how far away the object is going to be. What if we went to a higher magnification? So what would it take to get a magnification of 2,000? What would it take to get an overall magnification of 2,000? Well, if this is the overall of 2,000, then realize that there's always the eyepiece of times 10, and then times something or other. It would be the eyepiece would have to be times 10. The objective would have to be times 200 in order to get 2,000 overall. So with an objective of times 200, what would its focal length be in that case? So that would be this L over F0 equals 200. So F0 would be L divided by 200, or 16 over 200. And that is 0.08. Now that's centimeters. You might rewrite that as 0.8 millimeters. So what that means is with this objective, the object has to be less than a millimeter away from the lens. You've got to get kind of close. And certainly you get higher magnification than that. Lots of microscopes have times 400, and some even have go as high as 1,000. And then you have to get the object very close indeed. You might even have to be touching it. Some of them are designed to immerse the objective lens right into the liquid that contains the sample that you're looking at. Okay,